Just quick question. Do you even watch? Do you watch the videos? No? Yes or no? Okay. Just not. Just not. So I have the feeling I did something. I didn't do anything, everything in vain, right? Okay. You watch? Okay, hopefully. Okay. Okay, exponential function. An exponential function is a function where the variable, okay, this is important, where's the variable in the exponent, variable or the unknowns, right? Or the x, okay, the x in exponent, okay, so x in the exponent, x right there, okay, exponential in exponent, then you need a base, okay, so where x is the exponent and a is, this would be, this is a typo, a is the base. Okay, A is the base. Okay, and to be an exponential function, A, there's also a condition for A, the base. The base has to be greater than 0, first of all. Okay, most of the time. We're going to discuss the case when A is less than 0, but it turned out to be just a flipping of this one. Just a reflecting of this one. Okay, so we're going to discuss that. Okay. Unlike this one, keep in mind that this function, x to power a, is different from a to power x. Clearly, right? X to power a. That x to power a, what is that? What do we call that? A to power x, we just learned, exponential. Okay, and want to show you the difference, keep in mind that this one is different from that one. This one, where the variable, the unknown x, is the base, clearly is the base, right? Is the base. X is the base right there. Okay, it's on the bottom, is the base. Exponent, base, exponent. So this one is not that. What's this one? A polynomial. So that's a big difference. Oh, a power, right? A power. Okay. So that's introduction of exponential function. Okay. Let's bring up a very standard example. 2 to power x. Base 2. Okay. Base 2. Okay, let's investigating x. Okay, because base, we know base 2. Nothing to talk about. That's just a positive number, constant positive number. But x can change because it's unknown variables, right? So what happened when x is a positive integer? Let n be a positive integer. So technically you have 2 to power n, right? X equal n, but n is a positive integer. Do you know what's the integer? First of all, I keep saying that word, but do you know what actually a set of integer? What does it mean? How do you classify integer numbers?
It's a real number.
There. That is where I want to see the mistake there. Good mistake. It's a real number. That is a little bit over the head, abundant. Too big. Real number is really huge. A really big. Okay, real number is huge. That is real number. Let's say that real number. That means include every number. Okay, that every real number. Okay, something bigger than that. There's something even bigger than that. But for now, real number is that integer somewhere in the inside. So integer is just not real number. Same integer is smaller, more condensed than that. Smaller than integer. I'm smaller than real number. Real number, that means any number. 1, 2, 3, negative 1, negative 5, 1.5, 2.5, right? Decimal 1.3333, square root of 5, square root of 10, cube root, fifth root. That is real number. The moment any number that you speak out, that's basically real number. Okay, you can use your tongue to speak out that number. That's basically real number. But not all of that number. On the example I just mentioned, not all of them are integers. So what are integers? Integer is going to be a smaller version. In other words, integer somewhere in there. Can you give me an example of integer? Huh? Integer is technically whole numbers. Okay, integer is whole number. You cannot have decimal. 1.1, 1.2, that is not integer. 1.1, 1.2, 1.3, 2 point something, square root, those are not integer. Integer is just whole number. And it could be negative, positive. And even inside integer, there are another smaller version. It's called natural number. That's basically the positive. Integer number, you can have negative. Natural number, you only have positive side, you cannot have negative. You have up from 0 and above. Anything negative is not natural number. Okay. A negative combined with a positive, now you have integer. And between those integer, there's a bunch of decimal, right? You can list million, billion of number. I can put a billion, 100 of number 9s after number 1. Right? I can do this 1.999999999. I can put 100 of number 9s after that. What is this number? What is this number? It's close to 2, but actually what's the name of that? The set of these numbers. Rational number. Okay, so something bigger than this. Irrational is Q. Irrational number. Q. Okay, see the bigger. And outside that is real. Everything I just mentioned to you, every number I just tell you, those are real number. Something bigger than real number. Something also included real numbers in there. This is about math theory. That's really good. Something bigger than real number. Something beyond that. You study that. If you're in my 112B, 112A, you study that. You heard that. You did math with that numbers. Complex. Or imaginary number. There you go. Okay. So we are right here. We integer. We in the right side. So if n is those integer. Okay, so now just keep in mind integer is whole number. Okay, because that's why I include positive. Because integer can have negative number. That's why I say n be a positive number. Okay, so it could be, for example, 2, 5, 7, blah, 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 right? Any number, positive number. Okay. Then when you write 2 to power n, what does it actually mean? Just mean, okay, if you write 2 square, that is 2 times 2, right? 2 cube, that is 2 times 2 times 2, right? 3 times. So 2 to power n, 2 times 2 times 2. Many of them like that. But how many n times, right? Right. Okay. How about when n is n? I put a negative in front of n. A negative in front of this. It becomes a negative integer, right? Positive integer, put a negative in front, negative integer. So 2 to power negative n. When we have a negative in the exponent, what can we do? We discussed this last time. We did this with the power rule when you take the derivative. Remember this? What did you do? Actually, remember this? It was in your quiz. Right? Well, and what did you do to that 1/2? Right? Yep. Okay. So now when you have a negative in exponent right here, the exponent, the negative exponent, you can rewrite in this form. So if I rewrite, it's like that. All right. Okay. That basically, okay. 1. That number 1. Can I put an exponent to that? The beauty of number 1 is I can abuse it legally. I can abuse number 1. Literally. I can do anything I do with number 1. I can multiply, I can raise it, I can divide with number 1, right? You know that, right? And because when I write like that, I can combine them. And now suddenly this one look like this. And if I have to expand this. Okay. In other words, 2 to power negative integer. 2 to power negative integer is just 1/2 n times multiplication n times. Okay. 0. I don't think I need to talk a lot about this one, right? 2 to power 0. Okay. Rational number. Rational number. So 2 to power p over q. How can I... is there any way I can rewrite this one? Can I rewrite this? Rewrite this. P and Q. P and Q. Again, P and Q are just some number. Again, I borrow this example again. That will be 1/2. Where are those? Okay. Looking at the square root, I don't see number 1. I don't see number 2. So where do these numbers come from? Okay, we know it. Yeah, we know it. 1/2 because of that square root. But actually, why? Why 1? Why 2? Why not 3? Why not 4? Why not? Why 1/2?
The 2's like in the, like there.
What is the name of that thing?
I don't know what it's called.
Square. Literally, there is an invisible number 2. But square root is so common, right? People don't write number 2, but usually it's in the name, square root. Okay. Number 1 is right here. Okay. You have cube root. Okay, cube root, not that common, so we have that. Okay. Now, okay, if I replace that to number 2, okay, I have this. Right, I have that. I replace number 2, I have that. Now you have this. P over Q. If I rewrite in a root form, where do I put P? Where do I put Q? P inside or outside? Q? There. Okay. All right. So a lot of some of them very familiar, right? Some of them new, some of them, you see it again. Okay. Recon 113, huh? Okay. Okay, we investigate the exponent. Okay, we investigated the exponent. Now we're gonna investigate the base. Okay. Okay, now we're gonna investigate the base. So we have base 2, base 1/2, base 3, base 1/3. Okay. The base tell you how's the the function look like. Okay, earlier we talked about the numeric, okay, side, the numeric side of the exponential function. Now we're going to talk about the plotting side of this. Okay, so if I plot 2 to the power x first, I'm going to plot all of them on here. Okay, 2 to the power x. What does it look like? 2 to the power x. Okay, let's pick. Okay, let's generate. Okay, the best way to plot anything is just do the table. Let's pick some number. Actually here, x, 2 to the power x. Okay, and then we pick some number. Start with 0, right? 2 to the power 0. 1. So 0 give you 1. Maybe here. There. If I choose 1, 2. So 1, 2. Okay. And so on, right? You can see the pattern. You can see the pattern now. 2, I will have 4. So 3, 4. There. And of course, if I pick 3, I already run out of space, right? I cannot read it to 8. If it's 3, I will go to 8. I don't have enough space, but I know that it's somewhere up here. Okay, maybe somewhere in there. Okay, so if I connect the dot, I have that, something like that, right? It feels incomplete. What happened here? Okay, this is where you pick negative x, right? 0, 1, 2. Okay, let's pick negative. If I have negative 1 or negative 2, what do I have? Okay, 0 is 1 there. Okay, so how about I pick negative 1, negative 2, negative 3. I will have 2 to the power negative 1, right? And we just did the math. If we have negative, it becomes 1 over 2. Right. So when I have negative 1, when x equals negative 1, the function is a half. So negative 1 here, and a half is right there. So around here. So a half. So negative 1 and a half right there. I keep going with the pattern. I think just 2 numbers would be enough for you to recognize the pattern. 2 to the power negative 2, that would be 1 over 2 squared, that would be 1 over 4. And the 1 over 4 is just a quarter. So 1 over 4 is a half of a half of a half. Okay, so maybe here. Okay. You can see the pattern, right? If I keep going, the curve will approach 0. But let's say if I draw like this, is it correct? If I draw like this, okay, apologize, I'm going to zoom in. Okay, I'm going to zoom in. What's that? A root, a 0, an x-intercept. When I do this, that means the function intercept x. That means the function has 0, right? The function is equal to 0. Is there any number down here, any negative number down here that make that give you this? Is there any number? Okay, the smaller you pick it there, right? 2 to the power negative 10, put another 0, put another 0, put another 0, put another 0. But will it ever reach 0? No, right? No. In other words, it's like an asymptote. There. Yeah. Now it's a line. Okay. I don't want to lie. Okay. Curve. Don't touch. Hey. Okay. I'm not going to hold it. Yeah. Okay. All right. And you just give me one of very, very, very important property of exponential function. Exponential function never zero. This one is always positive. That is a very strong property. Exponential function always positive. It not even go to negative side. Remember, this is your function. This axis, this y-axis is always in here. It's never down here. It's never down here. It not even touch the zero. Exponential function always positive, no matter the x, no matter the exponent. Okay, it's always positive. Okay. By that analogy, I think you can draw 3 to power x, right? 3 to power x. Okay, so this is 2 to power x. 3 to power x will look something similar to this, right? Curve up, similar to this. But both of them, this one and this one. I'm talking about this one. Later I'm going to talk about this and this, okay? But for now, 2 to power x and 3 to power x, okay? 2 to power x, like this, the blue one. 3 to power x, very similar to this. But both of that one, I'm going to draw, let's say if I use a purple one, I'm going to draw something like this for 3 to power x. This 3 to power x will intersect this 2 to power x. Guarantee at one point. Where is that?
0,
right here. In the beginning, in the beginning, when you plug in 0, 3 to power 0 equal 1. In the beginning, exponential function always start at the same point. In the beginning, think about time. In the beginning, when x is 0, 3 to power x here. So you're going to draw something look like this. There. And one thing about 3 to power x, it increases faster. Okay, bigger base, you can do the analogy. You can see the analogy, right? The smaller the base, you increase lower. The higher the base, you increase faster. Okay. Now, I want you to spend maybe a couple of minutes. Draw them on top of this. Try that. Let's see. And again, positive. No matter what you draw, all of them will be positive. I'm going to use the red one, maybe the black one for this, the red one for this. Exponential function, always positive. Okay, try the 1/2. See what does it look like. Try the 1/3. What do you think? Oh, and just so that you know, all the notes for this semester already uploaded, huh? On the way, okay. On the way to chapter 5, okay. So every note is uploaded on Canvas. Okay, just so you know. Okay, for the other two, you don't have to precisely, just point in the right direction. Okay, you don't have to precisely correct to the number. Okay. There, brilliant. Yep. Okay. So x and a half to power x. Start with 0. I think everybody knows that's right there. Whatever the base, as long as the exponent is 0, you equal 1. So I'm not going to even plug in 0. 0 gives you 1. Okay. 1 and 2. That 2 point is enough. 1. 1/2 to power 1, a half. 1/2 to power 2, that means 1/2 square, a quarter. Right. So 1/2, a quarter. Connect the dot. And also I recognize the pattern. Right, you recognize the pattern. Do not touch. Do not touch. There. Okay. Okay. Right hand side look like that. How about pick a negative? Now pick -1. Pick -2. -1. That means 1/2 to power -1. 2. Okay. What is the property that I use there? What's the property? If you have a fraction to a power number, a negative power, you literally can flip that and change the power. Okay. And one thing is, when you ideally when you do exponential, you see a negative in the exponent, try to get rid of that first, and use some property. Okay, to get rid of that. So this is one of the property. Is a fraction with a negative exponent. Flip it upside down, then you can get rid of the exponent. That's what happened there. 1/2 to power -2. That basically 2/1 to power 2, right? That is just 4. Okay. So when it's -1, you have 2. Okay, -1, you have 2 right here. When it's -2, you have you have 4, positive 4 right there. Connect, and you get 1/2 to power x. Okay, I think you can get the idea. 1/3, right? Okay. Look at the red one and the blue one. Now I'm going to erase the purple one so you can see the picture. Look at them. I erase on the minor details. Okay, a bunch of irrelevant detail now. Just focus on the graph. Blue and red. 2 to power x. 1/2 to power x. If you want to make a connection between them, how do you say that? How do you put that in a sentence? Want to make a connection between the graph? How do you make them? How do you?
Like 1/2 raised to the x and 2 raised to the x are like transformations over the x-axis of one another, or the y-axis of one another.
Transformation over y. Okay, transformation is good word, but not good enough. Not detailed enough. Yes, that's technically transformation, but what would be the a better one? Reflect. Yes. Yeah, transformation, and then I want to use more specific word. They reflect each other over the y-axis. Very good. Okay. So that's why I erase the purple. I don't draw the 1/3. The purple 1/, that is 3 to power x. So 1/3 to power x, right there. Okay. Something I want you to get out from this example, from this one. Look at them. It's always above the x-axis. Therefore, it's always positive. Exponential function, always positive. Very strong properties. Okay. Because of this property, okay, people make money because of this property. Finance, everything in the real world. Finance, health, electric, buildings, construction. I've been writing reports. I've been writing analysis for small firms, for big firms as my part-time. In all of my firms, nearly 10 firms that I've been working with part-time. Never once that I haven't seen an exponential model. An exponential model. Everything in daily life is based on that look. Everything look like this. You see stock, but you see this, right? Right? Something like that, right? That exponential. And you see, okay, you see stock. Whoop. Right, okay. That's a panic sale. Okay. And a check, someone scoop you up. Sell it again. Okay. 2008 market crash. There. It doesn't look like anything like exponential. But how do they analyze? They cut it. That is one exponential right here. That's another exponential right here. That is an exponential right here. Another one right here. That is very steep exponential. That is another exponential. They chop it down into sections. They analyze, and that's what I do. Okay. Everything you see in the world, everything, if you plot the moment, you plot it in 2D like this. They are exponential. The parabola, you cut in half. Right side, exponential. Left side, exponential. Everything is about exponential. Everything, in other words, any equation, any function, anything that you've seen so far, that is the square root, right? Or something like this. That's basically exponential. Okay? Everything you see and you're about to see for the rest of your life is exponential. Some form of exponential. Okay. All right. Next, we see the pattern that. What do we see? When a is greater than 0, when a is less than 0. Between 0 and 1. Remember, the base, to be exponential, the base, first of all, to be exponential function, the base a has to be positive first. Okay, greater than 0, not equal 0. You don't have this. You don't have this. That's just 0. Right. So that's why the base, it has to be a positive. Okay. Then what happens when base is positive? Okay, base positive. This is what you have, right? 2 to the power x, 3 to the power x. This is what you have, right? Those are the examples. Okay. When a is positive, you have this kind of behavior. Right? And when you have negative, you have this kind of behavior. When I say behavior, what would be your corresponding response? If I ask you, what's the behavior of this one? Now we've been discussing behavior. Use the correct vocabulary. What would be the behavior of this one and this one?
Opposite.
Opposite. No. For each one. Now the opposite, we talk about that over here. We compare. But for this one, okay. Imagine you don't see this down here. You only have this. What is the behavior of this function?
Exponential.
Exponential, but exponential is the name, but more familiar term, more. Say it. Somebody just saw it. Just say it.
Increasing.
Increasing. Don't be shy, guys. Come on. Increasing. So when you have a base that is greater than 1, you have an increasing function. When base the base between 0 and 1, that is decreasing. Okay. Can I ask you this? So let's say this starts from 0. So there's every number before 0. Okay. And somehow exponential function clearly divided right here, 1. Okay. So after 1, okay, what happened at 1? First of all, what happened at 1? 2 to the power 1. 2. It's just a constant. It's just a straight line, right? 3 to the power 1, a constant straight line. So we don't care about how it happened at 1. That's why everything in here, everything over here. So if you compare the numbers in, okay, let's pick number. Let's compare the number in here versus the number over here. How many numbers are there? Let's try to compare that. How many number in here? What do you think? Just, yeah, infinity, right? A lot of numbers in there, right? Right? Infinity, huge. Okay, infinity number here. Why this one can be able to compare in here? To compare to this? Only this much. Only this much. How many number? Yeah. How many number actually exist in here?
There's an infinite amount of numbers between 0 and 1. There's like small and small.
Yeah. You see that gap? 0 to 1. That small gap contain equal number to this. That's one thing about math theory. And people still figure that out. Try to figure it out. Okay? For no reason. Just for the love of the game. Literally. Okay? All right. They don't have any time to do. Okay? So figure out why there between any gap. And also, it's some kind of really tripping. Between 1 and 2, again. The number, the quantity of the number in here equal this, 1 infinity. Okay. Now you've been wondering, you signed up for the wrong class, right? Why am I in here, right? But that's something to think about, right? That gap, if I draw is longer, a bigger scale, bigger x-axis, that's tiny, extremely small. Between 0 and 1, that's extremely small. This interval, absolutely very small. But this interval contains the number. I don't say the quantity of the number. It's small or big, I don't care. It's just about the number. Exists in here, this interval, equal the number greater than this, in this interval. And look at this interval, there's no stopping limit. It's just greater than 1. It never stops. This start for 0, it stops at 1. But they contain the same numbers. Okay. Theory, right? Theory. Next. Again, base A always greater than 0. Oh yeah, why did I say all of this? Basically, I just write right here. Okay. Thus, exponential function is always greater than 0 for all A and X. As long as A is greater than 0, as long as A is greater than 0, no matter the exponent, no matter the x you put in here, A raised to power negative a million still greater than 0. Okay, the negative exponent doesn't affect the sign of this one. It's always greater than 0. 2 to power negative 9994 number 9, or maybe 6 number 9, I don't care. I guarantee that is going to be positive number. Okay. Okay. So enough theory, enough dissecting exponential. Let's do some math. What can we do? If we want to do math with exponential, we did some of them already. The first thing we did is this, right? We did that, right? Some rules, some properties. Here are some more. Okay. Base of a sum. Okay. Exponent of a sum. Exponent of a sum. Okay. Exponent of a sum. I can split it out. split like this. The base remain to be the same, base A. Okay, exponential of exponent. What do you do with the exponent?
Multiply.
You multiply. Don't add, huh? Keep that in mind. You multiply. Okay, how about this? Divide. This one you can split out one by one. Same exponent, different base. Same exponent, different base. Same exponent, different base. You can combine this. Same base, different exponent. Different exponent. You can do like this. Okay. All right. Okay. So apply these. We're gonna try the example down here. Okay. I do one, you do the rest. How about that? Okay. That's right. Simplify. Okay, what can I do? Exponent of exponent, right? Exponent of exponent, so we're going to multiply them. Okay. Right? That number 3 there. Yellow. Right? No. Where's the mistake? I just did that exponent. That number 3 is this one right there. Exponent. Multiply them. The 2. I heard somebody say 2. Yes. The exponent 3, it go inside here. Okay. Usually, when you have exponent of some number, if that number have a positive, have a negative sign, I highly recommend you put a parenthesis. Okay, why? Why do I do that? Okay. Tell me what would be your answer to this? Negative 8, beautiful. Keep going, be confident. Are you sure?
-4.
Because the square only applies to this. This is positive 4. Okay. Keep that in mind. The parenthesis means something. Without parenthesis. Because the negative of the cube, okay, that's the odd power, the negative, not really affecting. But if you have an even power, it's tell. It happen a lot. Okay, it tells something, okay? All right, and I saw this. I saw it many times in the quiz when you distribute. When you distribute, I remember somebody did this. Oh, no, never mind. I don't want to go that way. Okay, I don't want to recall your pen. Anyway, keep going. So we have that parenthesis. And yes, you just tell me that is negative 8. X to power 5 times 3, 15. Why? Clearly. z to power 3 times 3, 9, and then there you go. That's it. Okay, that's the answer. Okay, now try the rest. Try the rest. I'm going to zoom out. Where's B? Actually, not. Actually, try your homework. That's your homework. Okay, it's your homework. This time, ladies and gentlemen, look carefully. Look for your homework. Okay, look carefully. Last time, I gave you 2 problems in the homework. Nearly half the class submit only 1 problems. Okay, nearly half the class submit only 1 problems. Okay, literally H and W. Somehow I thought did I write Japanese? No. Did I use Korean? Homework here, right? No, didn't know. All right, it's actually H and W. Right. I thought for a moment I wrote Cambodian or something. No. Right. So homework, English. Right. So look for the homework. Do. Okay. So this section 3.1, just so you know, if you see this one in the handout, that means this section you're gonna do in paper. There's no online. Okay. So do on paper or do over here. You can export that. Do over here, and export only this one. Okay, this one. I don't need those. I don't need down here. Just the work over here. Okay, and it's your homework. Actually, may as well try that. Go home, copy and paste. Okay, leave it there. Okay. I think it should be simple enough for you guys, right? Okay, limit at infinity. Okay. The best way to discuss limit to something new, something we haven't seen before. The best way to discuss them, to learn about the limit at infinity, plot it. 2 cases. You should know, okay, now I hope you familiar with these 2 plots. When A is greater than 0, you have that. When A is between 0 and 1, when A is greater than 1 and between 0 and 1, you just basically have an increasing and decreasing function like that. Okay. So limit at infinity. When asked limit at infinity, you need to answer how many things? How many things do you need to answer for this question? How many things you need to answer for this one?
A theorem.
Okay, it's okay. Keep thinking. Limit at infinity. Limit at infinity. What at infinity? Okay, the question is, you want to know the limit at infinity, but what at infinity? What at infinity? Limit of what at infinity? The? Go ahead, somebody just say. A is the base, okay, close. Another one.
The value of the f of a, I guess.
Uh-huh.
The value that it's approaching, the y value that it's approaching.
The y value when it's approaching, when
When
When-
a goes to infinity.
When x go to infinity, that is what it means, limit infinity. When x go to infinity, limit of your function. And because that's why I asked you, how many things you answer? I need to answer this. When x go to infinity, x go to infinity, which direction? How many directions? There are 2 directions. You need to answer 2 things. X go to positive infinity. X goes to negative infinity. You need to answer 2 things. In other words, positive infinity, negative infinity. Limit a function when x go to the right, x go to the left. Copy and paste down there. For each one of them, I need to answer these 2. Okay. Okay. One by one. Positive infinity, negative infinity. Now we just look at the function. When you write this, it's easy to see, right? When x go to positive infinity, right, that is your x, go positive. Where your function going? Positive infinity, clearly. When x go this direction, your function shoot up. In other words, this one two to power x. Look at that x. That x, the bigger the x you put in there, the bigger this number, right? That exponential function. Then you function, the whole thing, this is your function. This is your x. X get bigger. This thing get bigger. Then what happens when this x gets smaller? That means x go to negative infinity. You plug in a very small number. You can tell from here, or you can tell from analyzing this. What happened?
Very small number close to 0, but never equal to or less than 0.
Okay. So what will be your final answer? You're gonna go to?
Which is 0.
You go to 0, right here. Remember, maybe put in negative infinity here, right? Whatever down there. The value that you plug in there is going to be extremely small, which is 0. Okay, if I flip, okay, I think you can answer this, right? I want to do this in maybe 10 seconds. I'm going to go around and look, answer that. Feeling, 10 seconds. 10 Mississippi, A, B, C, 9 Mississippi, A, Mississippi. What will be your answer? Okay, 7. Wonderful. Close. No, correct. Technically, go to positive infinity. Your function goes to 0. Correct. But on the left, when x let's say if I pick x down here, somewhere in here, where will be your function? If you pawn it, where will be your function? Where will be the pawn corresponding? So up here, right? What do you think this number will be?
Infinity.
Infinity, not negative. There. What do you have? Okay, 0 and okay, I see. Okay, the first one everybody got 0. That is good. That's good. Clearly, there. X go here. The function go to 0. Clearly, very 0. But here, this direction, when x go to negative infinity. Let's say I pick a number right here. I see two different answers. One is positive, the other one negative. Okay, I see two answers from you guys. Only one of them stay. Pick a number down here, extremely small. X down here. Maybe negative 20. Right? Negative 20. 0, negative 1, 2, 3, negative 20. Plug in negative 20. You go up, right? Somewhere in here, right? That should be somewhere in there, correct? What do you think that number? The value of that number. Just positive or negative? Positive. And now think about a quantity. 2 to power negative 20 is something. Something to power negative 20 over here. Very huge. Positive. Okay. Good. Moving on. Apply that. Think about that. Think about doing this. Limit 2 to power x minus 1 when x go to infinity. In other words, think of it like this. You're about to plug in a very huge number right here. Then what happened to this quantity? Right? That's exactly what we study limit for, right? When x goes to infinity, when you plug in huge x here, 2 to power infinity. Give me the answer. 2 to power infinity. Infinity, and then you subtract 1 from infinity. Still infinity. Easy, huh? Easy to analyze, as long as you understand the nature of exponent. Then what happened when I flip the direction, not the sign. I flip the direction of the x. Now go to negative infinity. Now try to visualize that. Try to imagine that. And put down your answer. What do you think? What would be your analyze? Not just the answer. What would be your analyze? What would be your, conclusion? Now x go to negative infinity. Imagine plug in a very small number, okay, 2 to the power x. This alone. What do you think this number be?
What's this?
2 to the power negative infinity. 2 to the power negative infinity. 2 to the power negative 100. This before the negative one. Okay, don't think about this. This one alone. That would be from the previous page. Where that would be somewhere over here, right? The function go to 0. In other words, that basically 0 minus 1. Too quick to conclusion. Okay, that's a good way to plug in. Okay, but you try that. Now try be bold, be more imaginative. Negative. You're gonna keep plugging in 3, 4, 5 on the way to that. Think bigger. Now plug in 200, 500, 1,000. See what is changed, and it's gonna change quickly. Okay, so I have 2 kind of answer. I walk around, I see 2 different answers. I see, no, actually I see, I see 2 answers, 3 answers. I see negative infinity, I see negative 1, I see 0. Any other answer beside this? Okay, so you are within these 3. The correct one, drum roll please. It's negative. Yep, negative 1. Why is that? Okay. I like how you put in here, you analyze. Okay, you know that you plug in. But when you plug in, try to analyze it. Try to, reason yourself, not to me, reason to yourself. 2 to the power negative infinity. What do I get from this quantity? 1 at a time. 2. Infinitely small number. What do you mean? Now we have 2 concepts of small. What does it mean by small? Okay. It's like you learning psychology, right? What does it mean by small? 0.111 That is small. There is another number that also considered to be small before you get here. Negative. That's also small. A negative. That's also small, right? That's also small. Which one do you use talking about? Okay, the top one. Okay, so in other words, really close to 0. Okay, so that first quantity, this one, usually when I say approach, we're going to do this. You go to 0, And then behind that one is -1. Ratio -1. Okay. So good. Okay. The next two is your homework. Okay. Again, I'm gonna highlight. Okay, I'm gonna highlight. Okay, so that's those two. These problems take you maybe just a minute or two. Just it's about reasoning. It's not about mathing in here. No, just reason. Okay, and you go in two different directions. They're not the same, huh? What happened is positive. What happened is negative. Think about that. Okay. Natural number. Today we talk a lot of things, a lot of theory. Okay, a lot of theory. Natural numbers. Raise your hand if you heard this one. Before this class, I talked about this one a couple of days ago, right? Last week. Before this class, have you ever learned about natural number? Raise your hand. Okay, raise your hand. Okay. So most of you learn about natural number. Okay, that's good. I'm going to move fast. Natural number is a base. Base among all the base. Base E is the most common one. E, yes, the name of E is natural number. Natural number is called E. And can somebody give me the value of E using your calculator? Just calculator. Pressing E 2.7. 7.
1.8.
Okay, 2 around there. Yeah. See. So in other words, it's just a constant. First of all, we have to establish it's not a variable. It's no more, no less than a constant. It carries the same identity like pi. It's around 3.14. Right? Maybe another, okay, those technically these are called constant, right? Universal constant to be exactly. So everybody agree these value, we assign a letter, a symbol to them. Give me another one that we agree. 5?
Is it?
Row? Which? Okay. So maybe that one, I don't know. Okay, somewhere. Okay. Maybe there's and there, but I don't know that one. Okay, so row. I remember row right this, right? But I don't know that number. Okay, maybe another number. Something also very kind of familiar to you in physics. G? Right? Around 10, right? Or around 9.8 meter per second square, right? Gravitational constant, right? Because those numbers, think about that. So I'm trying to give you an example, yeah? Rho, do you know the value of that?
It's
Around.
like root 7 over 2 or something.
Okay, root 7 over 2. Okay. Okay, around it. Right. So what I'm trying to say, they are just a bunch of constant, okay? But they're important constant. So when you take derivative, when you take limit, when you do the math with them, you can treat it like a constant, okay? And how do they actually come up with this? How do they actually come up with this? E, the true value of E is this. Limit 1 plus x to power 1 to power x. Yeah. Did I put it correct? Yeah, correct. Yeah, this one is no. This variation easier to see. 1 plus, okay, 1 over x, that should be 2. No. Oh, that's 1. Okay. So this is a formal definition of natural number. But for us, for the sake of calculus 1, I only need you to know that E first is a constant, second is around this number. That's it, 2.7. Okay. Then, because E is 2.7, that's why I need you to know. How do you actually graph this? What does it look like? Now you know E is around 2.7.
It's like an exponential. At
Yeah.
1, it's going to be 0.
So technically, this direction or this direction, that's first thing we have to establish. Left one or right one? Go to the left or go to the right? Go to the right, that's one thing. And does it still follow the rule that the y-intercept is 1? Still, right? Think of this like this. Around 2.718 to power x. Okay. But what is the actual position of that one? Earlier, okay, I'm going to scroll up, huh? You know that, right? You can easily draw it. Earlier, we draw this. We drew this. 2 to the power x, dot. And then we draw 3 to the power x, which is the purple one. That. Okay. Because 2e to power x is around 2.78 to power x. Look at that number. That's between 2 and 3, right? So the plot of e to power x will be squeezed somewhere in the middle. If you actually draw that. It's somewhere in the middle. The base. 2 to power something, 3, 2. Okay. Okay. So it is this. Why E so special? Now here's the why. Try it again. Why E so special? This the sentence down here. Y equal e to power x is the exponential function whose graph crosses the x-axis at the point at the point 0, 1 with the slope what do you think?
E to the x.
Close. The slope. Okay, in other words, okay, right, okay, it had many slope. Slope here, slope here, slope here. The special slope that we are talking about right here at the y-intercept. If you draw a tangent line right there, 0, 1, that tangent line had a special slope, special number.
1.
That is the only exponential function. The slope at 0, 1 is 1. And because of that, with more proof, okay, slope right here, m of t equal 1, using a bunch of more proof, blah, 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 you come up with this result. And it become one of my favorite formula, which is, because the slope is 1, you have the same derivative everywhere. Okay, that's one of the things special about 2 to the power x, the base e. Okay. All right. So keep that in mind. Only the slope at 0, 1. Slope at 0, 1 is 1. Okay. Limit of e to power x. E to power x. Okay. E to power x. I will draw like this. E to power x. Can you write out the limit? X approach infinity, but now I know that which function I'm talking about, right? E to power x equal limit x go to negative infinity, e to power x equal, can you answer that? Okay. And if you have a negative, okay, if you have a negative x, e to the power negative x, same idea. I think you can answer this. I mean, e to the power x when x approach negative infinity. It's like we discussed the whole exponential again. We revised the whole exponential again, but specifically for the case base e. Okay, it behaves the same. It behaves the same. The big difference is the slope at 0, 1 equal 1. Okay, it's still an exponential function. It follows on the rules of exponential function. The special thing about that is slope at equal 1. And because of that, that is right. Even though, okay, it sounds so normal, because of that, we able to prove that the derivative of e to the power x equal e to the power x. Okay, I think you can answer this one right down here, huh? Okay, let you work on that. Okay, use that to evaluating the limit of this. Evaluating the limit of this. Okay, I'm going to do the first one. E to the power 1 over x. E to the power 1 over x. First thing I want you to do is change, okay, that 1 over x. It's not easy to recognize, easy to not analyze, right? Can you analyze that? 1 over x when x approach 0 from the right. 0 right here, x approach 0 from the right. 0 right here, right, left. Try to imagine that, try to analyze that. And then 1 divided by that. And then e raised to that. Think, analyze that. Try to plug in a few number in imaginary. Imagine some number, plug it in, do the math. 0.0001, blah, blah, blah. And 1 divided by 0.0001 give you what? What do you think? Okay, what would be your answer? 1. 1. 1 for 1 over x or 1 for the whole thing? Right. Keep going, okay. So I just, 1 is not an answer. Okay, now you can think of another one. Okay, you can eliminate the 1, the option. Okay, the option 1.
Isn't that undefined?
Huh?
Is that undefined?
Undefined? Undefined, no. Because if approach 0 from left and right, then it's undefined.
Oh.
This one 0 from the right. Okay, so that was defined.
Positive infinity.
Positive infinity. Anyone have the same? Okay, any other answer besides positive infinity? Anyone say 0? Okay. It's positive infinity. Okay. Do you know why it's positive infinity? Okay. Do manually. I'm going to do it manually. Plug in. Because 0 from the right, I want you to choose a number on the right of 0 that really close to 0. What would be your first thought? 0 on the right. 1, okay, that's one option. That's E. Okay. Closer than that.
0.0001.
Okay, calculator. How much it is? One, okay. Just don't use the calculator for this. Just this. 1 over 0.0001. 1 divided by 0.0001. Is that 1,000? Right? 10,000? Oh, 40. Okay, thank you. 4,000. E to power 10,000. Huge or small? Okay, so the closer I get to 0, this fraction being bigger, e to something big is bigger. Therefore, this limit go to infinity. Okay. Any question? Okay, good. We times okay. Maybe another example. You can practice this. This is your homework. I'm gonna highlight. Let me give you derivative. Okay, let's finish this one and then we can have a break. Okay, now last thing. This section, this subsection, this number 5, is actually the one we're going to use for the rest of the semester, the derivative of exponential. The previous 4 give you a taste, give you an introduction to exponential. We don't apply them a lot. The thing that we're going to apply is starting here, this box right here. To be more specific, these two. Like I said, B is A, extremely common. You're going to see from now on, when you ask you to take the derivative later, every other example, I keep bringing up these. Okay, I keep bringing up e to power x. Okay, start with this. Right? Right or wrong? Oh, man, come on, we're 3 weeks in the semester. You're gonna have the sense to debate, Multiply by? There, chain rule. Okay, e to power x, similar to this. E to power x and e to power x, but any other base beside e. Any other base, you have the same, but you're going to multiply ln of a. Okay, for those of you who don't know, ln is logarithm base e of a, which is what we're going to discuss in 3.3, logarithm base e. For now, it is what it is for now. That's right. If you don't know that, logarithm. We're gonna discuss logarithm in 3.3, which is tomorrow. Okay. So a to the power x times ln of a. And inside the logarithm also have its own rule. Logarithm also have its own rule. Where ln of e is called natural. This one. Now, logarithm base e, my bad, base e, aka natural log. E is natural number. Then logarithm base e is called natural log. Okay, natural log. Combine both of them. Natural log of a natural number. Okay, I'm about to bite my tongue. Natural logarithm of a natural number is 1. Okay, that is a property. Therefore, if you look at this example, if you look at these two examples, they're basically the same. But this is a special case of this one, a special version of this one. If you have e to power x, you replace the e to here, right? E to power x times ln of e 1. That's why you have e to power x. Okay, it's just a special version. Here, a to power u times ln of u times u over dx. Chain rule. Okay. Oh, time ln of a. Why it keeps messing up? Time ln of a. Okay. Okay. Memorize this. Okay. How many examples am I looking at down here? I'm gonna zoom out a little bit. 2 to power psi. Maybe. Okay. Let's do one example. Can I move on? Okay. Just do an example. Find the derivative of this. Clearly, that the exponential. That is not, first of all, this is not this. They are not the same. I say that from the beginning. Therefore, their derivative are not the same. This one gives you 2x, right? This one gives you 2 to power x times ln of 2. Right? They're not the same. Derivative is not the same. Different, completely very different function. I'll give you something more. This one look like this, right? 2 to power x. X squared is a parabola. See? Everything about them is different. Everything about them is different. The graph, the plot, the derivative, the way they write. Therefore, okay, then you have to recognize which function are you working with. 2 to power psi, that is a to power u, right? You want to take the derivative of that. A in this case is number 2. Okay, I'm going to write the formula again in case you haven't memorized. A to power u derivative is going to be a to power u times ln of a times du over dx. Okay. U is that side. A is that number 2. So follow the pattern. 2 to power psi of x times ln of 2 times d over dx of what? Of psi x. Okay. Just plug in. Plug in literally, plug in there. Plug in there. Okay. 2 to power psi times ln of 2. That would be cos x. Okay. We're going to come back at 11:15. Okay. 11:15. Finish this one. We're going to move on to 3.2. Okay.
I will.